This video will cover a review of Chapter 3, specifically Sections 3.1 through 3.4. Section 3.1, we learned about the quadratic function and looked at several of its properties, and we worked towards graphing it. So again, Section 3.1 is on the quadratic function. Let's go over a couple problems and see how to solve them. The first four questions will give us a variety of a review associated with graphing quadratic functions. We're going to first determine where the parabola opens up and down. Later in the chapter, we call this the end behavior. And again, because a quadratic function is even degreed, the leading coefficient will strictly determine if it opens up or down. We'll look at the vertex, both using transformations and the formula negative b over 2a. We'll remember that the axis of symmetry is a vertical line through the vertex, specifically in the form x equal to h, where h is the x value of the vertex. So we'll also remind you that k is the y value of the vertex. To find the x-intercepts, what we essentially do is just solve setting the function equal to 0. And we've done this several more times with more complicated functions. For the y-intercept, we'll simply plug in 0. And then, of course, the domain and range. Well, the domain here is going to be negative infinity to positive infinity for all polynomials, and the range will depend on the vertex. So let's go through several examples and recall how to do this. All right, so in the first case, and I'm not going to label them A through G here below, I'll just simply go through all of the steps in a way that feels natural. All right, so determine whether it opens up or down. In the case right here, the leading coefficient is going to be -1. So the end behavior is up, or in the case of 3.1, we just simply said opens up. The vertex in this form, we need to go ahead and use the formula negative b over 2a. In this case, b is 2, so it's -2 over 2 times -1. So this is just going to be -2 over -2, or simply 1. So k we obtain by just plugging what we get in for h. So f of 1 is -1 squared plus 2 times 1 plus 3. Or this is -1 plus 2 plus 3, so 4. So we have our vertex now. Our vertex is just the ordered pair, 1, 4, h and k. The axis of symmetry, or I'll just say AOS for short, is a vertical line. So it's x equal to going through the vertex, with this case is 1. Just to pause and maybe graph what we have right now, it'll be beneficial because it'll help us determine the x-intercepts. So the vertex is 1, 4, so we'll go ahead and put that up in the first quadrant. The axis of symmetry is a vertical line going through x equal to 1. So again, don't forget that the x equal to part is required for the axis of symmetry. And we are opening down, so we are going to have some x-intercepts. If we were opening up, then we could just simply say none, but let's go ahead and now find those x-intercepts. So I'll take the negative x squared plus 2x plus 3 and set it equal to 0. Let's zoom back in here. Remember that whenever there's a negative in front, you should go ahead and just factor that out, and then just go ahead and solve what is left. So again, if you were to distribute this back through, you would get back to where you started. So all of the signs ended up changing. So a negative comes down, and then the factors of -3 that add to -2 are x minus 3 times x plus 1 equal, and that's still equal to 0. So x is equal to +3 and -1. Zooming back out to look at the graph, if we just do a sanity check, there's +3, there's -1, and we do have symmetry. The y-intercept, we go ahead and plug in 0, so it's simply going to be -0 squared plus 2 times 0 plus 3, or simply equal to 3. For the sake of this review, I'm going to simply just observe that whenever we're given a polynomial in this case, a quadratic function in expanded form, I'll just go ahead and cancel everything out, and the constant, the c term, will be our y-intercept. Putting that there, it does seem to align with what we know about the symmetry. So determine the domain and range. So the domain, as stated above, is all real numbers. And the range, because it's opening down, is going to go down to negative infinity. And the highest will go as the vertex, which is 4 with a bracket. And just remember that 4 is the k value. Connecting the graph, we can use symmetry to get this other point. Connecting the graph in a smooth continuous curve that is parabolic shape. Let's try that again. We'll end up with the graph as, oh, come on, it's not autocorrecting. Let's try it one more time. All right, and we'll end up with a graph that is shown right there in blue. All right, so in the case of number 1, it was given to us in the expanded form. And number 2, we don't need that formula for the vertex because we can just use transformations. So we'll go through everything again. This in front is going to be a negative. So again, the parabola will open down. The vertex here, the h, is going to be the value with the x, but remember you need to change the sign. So h is -1, it's a shift to the left, and k is going to be 4. So that is a vertical shift. So our vertex here is just going to be -1, +4. -1, +4 right there. So we are opening down, so we will need to find our x-intercepts. But our axis of symmetry is just x equal to -1. It is just a vertical line going through the vertex. All right, setting the polynomial or the quadratic function here equal to 0. Subtract 4. You end up with a -1, or negative x plus 1 squared equal to -4. Divide both sides by negative, you get x plus 1 is equal to +4. Oh, still squared, +4. Taking the square root, you get x plus 1 is equal to plus or minus 2. And subtracting 1, you get a -1 plus or minus 2, or x is equal to -1 plus 2 is +1 and -3. So +1 and -3, we maintain the symmetry we were expecting. So there's our x-intercepts. Our y-intercepts, we plug in 0. We end up with a -0 plus 1 squared plus 4, which is simply 1 plus 4, or 5. So there's a little typo there. It should be -1 plus 4, so it's 3. And what made me think about that was if I put this here, it clearly would not match. So I went ahead and checked my math, and I did verify that I did make a computation, which I then fixed. All right, and again, the domain, all real numbers, are -infinity to infinity. The range opening down, so it's -infinity to the vertex is 4, and let's go ahead and connect them in the parabolic shape. It doesn't seem to want to autocorrect correctly, but second time we got it there. So there is the graph for number 2. Let's see what the next page will encounter. So in the case of this one right here, we are again given it in a form where we can just use transformations. This time it's positive, so it's going to open up. The vertex, h, is going to be a positive one here because whenever it's with the x is opposite, so it's going to shift it to the right. K is going to be equal to 3, so our vertex here is in the first quadrant, 1, 3. The axis, so I'll just go ahead and write again, the vertex is the ordered pair, 1, 3. The axis of symmetry here is just x equal to 1. And here's a nice little shortcut. Notice here in the first quadrant, if we open up, we will never hit the x-axis. So I'll just simply say that there's no x-intercepts, and that is fine. If you were to set it equal to 0 and solve it, you would end up finding an imaginary number, and we're graphing on the real plane. The y-intercept, f of 0, is equal to 0 minus 1 squared plus 3, which is just going to be 1 plus 3, or 4. So that is consistent with what we're expecting. We can use the axis of symmetry, which is the vertical line through the vertex, to go ahead and get another point to get the U-shaped parabola, and just autocorrect that back to the appropriate points. Again, the domain, negative infinity to infinity. And the range, this time, because it is opening up, the range here is going to start with a vertex. So it's going to be a bracket with the k value, or 3, and going up to infinity. All right. So number 4 is going to be back to its expanded form. So the leading coefficient is negative, so it's going to open down. And the vertex here is going to be, well, h is going to be negative b over 2 times a. So it's going to be negative 2 over 2 times negative 1, which is negative 2 over negative 2, or positive 1. K is going to, when you plug that back in, the h, you'll find k. So it's negative 1 squared plus 2 times 1 minus 2, which is going to give us a minus 1 plus 2 minus 2, or minus 1. So here we have our vertex, which is going to be 1 minus 1. So it's now in the fourth quadrant. Fourth quadrant, opening down, you can see right here, there's going to be no x-intercepts. The y-intercept we'll find by plugging in 0. Oh, I forgot my axis of symmetry, so let's go ahead and slide that down. So the axis of symmetry is x equal to 1. F of 0 is minus 0 squared plus 2 times 0 minus 2, or minus 2. So that'll be right here. Symmetry will get us that other point. And we'll go ahead and get our parabola. Not cutting that or curving that enough. Let's try that again. All right. I'm not going to draw the axis of symmetry this time. We've done that several times. The domain, all real numbers. The only thing that differs here from the standard is the range is going to be, again, negative infinity because it's opening down, up to the vertex, which is negative 1 for the k value. So that is a good review of the quadratic function. There was a few other observations that we can go ahead and make, just basically for 5 and 6, we're asked to determine if it has a max or min. Remember, this all depends on whether it opens up. It looks like this, so we have a min. And if it opens down, we end up with that shape, so we have a max. The coordinates of the max or min is simply going to be the vertex. So the coordinates this time. So the coordinates are just going to be the vertex, the h and k. And the domain and range, we can simply, domains all real numbers. Range will depend on whether it's opening up or down. So there's really not a whole lot more new here. I would encourage you to pause the video and make sure that you can go ahead and get through those. You'll go ahead and just need to find the vertex to answer part B, and then your answers to part C will depend on what you said for part A. All right. Section 3.2. For each of the following, answer the following questions, or each of the functions answer the following questions. We're asked to find the zeros, determine the multiplicity of each zero, find the y-intercept, and graph the function. And honestly, there's a lot of kind of implied steps right here. So that's a nice guide, but I'm going to go ahead and go through everything in a way that we similarly did in the actual lessons. So I'm going to start with the degree, the leading coefficient, the end behavior, finding the x and y intercepts, and getting the multiplicity and touch and turn, and even maybe briefly saying a little bit about symmetry. All right, so again, there's a lot to do, so you may want to just kind of separate this space into two halves. So the degree, when you're in expanded form is the sum of the multiplicities. So it's going to be 1, 2, and 1. So the degree here is 4. It is an even degreed polynomial, so we'll use that in a moment. The leading coefficient is the number in front. I'm not going to try to hide the leading coefficient. The sign will be right there in front. So it is a positive 1, and because that is a positive number, we can state the end behavior here is simply going to rise to the left and rise to the right. You're fine using the errors on the test, but make sure you are okay with all of the cases. All right, to find the zeros, you'll set the polynomial x minus 6 times x minus 3 squared times x plus 1 equal to 0. And in the factored form, it's easy to say x is equal to 6, 3, and minus 1. So our zeros here, I'll just do z for zeros, are putting in order, minus 1, 3, and 6. The multiplicity m for each of the zeros comes from, again, the exponent on which we obtain it. So 6 came from here, so its multiplicity is 1. The 3 came from here, so its multiplicity is 2. And the minus 1 came from here, so its multiplicity is 1. All right, so what happens at the x-axis is whenever the multiplicity, so this number is odd, it will go ahead and cross. This number 2 is even, so it'll touch and turn at 3. So touch and turn at 3. And again, 1 is odd, so it'll cross at 6. The y-intercept in this case, you're going to go ahead and plug in 0. So you'll get a minus 6 times a minus 3 squared times a 1. So you end up with a minus 6 times 36. And let me just check this off to the side. For number 7, that is going to give us a minus 54. So that's going to be way down here. I'll just go ahead and write maybe a little tick mark right there. There's no symmetry here. The fact that it's not stated, I wouldn't stress too much about the symmetry. So let's go ahead and graph this. But there is no symmetry here. I'll just make note of it. All right. So we have a 6 here. We have a, well, let's see, minus 1. 3 and 6. I like to start by putting my zeros or my x-intercepts. I'm going to rise to the left, rise to the right. So I'm going to start and I'm going to cross through this one. I'll come down, I'll hit minus 54. I'm going to come back up, and at 3, I'm going to touch it and turn back around and then come back through. So a couple of things to observe. The max are the minimums right here. It does not matter where you put them. We don't have the skills in this course, or I should say the tools in this course, to find those. So wherever you put them is fine. The other observation that I want to make sure you remember is that the graphs of polynomials are smooth and continuous. I think we have a few examples a little bit later. All right, so now that we have an example in this video recorded with a lot of the details, I may not go in depth on the next one. I'll just simply walk through how to approach them. So on number 8, this one, the degree is going to be the sum of the multiplicities. So those are the red numbers. The degree here is again 4. The leading coefficient is the negative 2. So it is a positive, it's an even degree with a negative leading coefficient. So the end behavior is going to be down to the left and down to the right. It's pretty easy to just look at the zeros in factored form, but just remember that when you set this equal to 0, this minus 2 times x squared equal to 0 is going to give you x equal to 0 as a 0. So our zeros in order are going to be minus 3 from the middle factor, 0 from the x in front, and positive 4 from the last factor. The multiplicities are going to be 1, 2, and 1 respectively. The x-axis behavior is that it'll cross at -3, touch and turn at 0, and a cross at positive 4. The y-intercept here is that when you plug in 0, because of this 0 in front, everything will just be 0. And there's, again, no symmetry. To actually figure that out, you would have to FOIL all of this out, and you would realize that you would have both an x to the 4th plus something with an x cubed, but a 4 and a 3. One is odd and one is even, or so because you have mixed even and odd exponents, there will simply be no symmetry. So my zeros are -3, 0, and 4. My y-intercept is the same as my x-intercept. I'm going to fall to the left and fall to the right. So I'll go ahead and cross through the first 0. Don't care about that max. Come down, touch and turn. Don't care about this max. Come back down. And there is our graph in a smooth continuous curve. All right. In the case of number 9, the degree here is going to be 3. The leading coefficient is going to be 1. Again, these are all understood to be 1, so that's where this 3 came from. An odd degreed polynomial with a positive leading coefficient will have an end behavior that'll fall to the left and rise to the right. If you do not know your cases yet, you do need to spend some time memorizing them, and hopefully you could recall them based off of the graphs of the x squared and x cubed and the reflections that we discussed back in 3.2 notes. The zeros here are just going to be in order: -3 from the first factor, 1 from the last factor, and 2 from the middle factor. And again, a factor is just things that are being multiplied together. So that's are all being multiplied. The multiplicity, as stated, are 1 in each of the cases. So the x-axis behavior, it'll simply cross at each of those zeros. The y-intercept here, when you plug in 0, you end up with a 3 times -1 times -1. So it's going to just be +6. Check my notes, make sure I haven't messed anything up. Okay. I think if you, and again, I checked the answer key. So again, this is the y-intercept. This is also as a point, 0, 6. So don't, either one would be accepted on a test. Just a little bit of a note about the answer key. So there's no symmetry here. To see that, you would have to FOIL it out. Again, just having some experience with this, I'm comfortable kind of mentally going through that and realizing that I'll have mixed exponents. So hopefully you've noticed, you've done enough practice to see that. So let's see, we have -3, that's -2, so -3, +1, and +2's right there. Falls to the left, rises to the right, y-intercept of +6, and we cross at each 0. All right, so those are 3 examples where we're given it in the expanded, or excuse me, the factored form. So we'll look at some expanded forms a little bit later. Here's what I was referring to earlier. Notice that the graph of a polynomial, it must be both smooth graph and examples. But also remember that maybe I'll add an extra one right here off to the side, that if we have a graph of the absolute value function, the absolute value function simply looked like the f of x is equal to the absolute value of x. This is also a no. So this one is a yes, it is smooth and continuous. This one is not continuous, nor is C. D is not smooth. E is, F is, and again, this G right here that I added, the absolute value of x, is not. All right, so we're now going to be looking at 3.3. 3.3, we learned about synthetic division, which was a way to find zeros when we weren't able to factor. So if you're given it with a divisor with an x, you do need to go ahead and say, okay, change the sign, so 2 will be in that leftmost corner. The coefficients, make sure that you're not missing. So there's x cubed, x squared, x, and no x. So those, nothing is missing. So we end up with 5 minus 6, 3, and 11. And there is our setup. Leading coefficient comes down, so I drop the 5. I multiply 2 times 5 to go ahead and give me 10. And that the product goes in the next column, and then I add down the columns, so that's going to be 4. Repeat, 2 times 4 is going to give us an 8. Add to get 11. 2 times 11 is going to give us a 22. And add to get a 33. And I always like to box in this last one, as it indeed is our remainder. Putting this, remember that we do reduce the power by 1, so it's now going to be a 5x squared plus 4x plus 11 plus 33 out of another x minus 2. In the case of number, and again, this is our answer. We didn't need to do anything more with that. In the case of number 12, we do have some missing terms. So observe that we don't have an x cubed. So I technically should rewrite this as 4x to the 4th plus 0x cubed minus 4x squared plus 6x and plus 0. We're missing a constant, but it's still divided by x plus 4. So 4 minus 4 goes in this box in the upper left-hand corner, changing the sign. Then we have 4, 0, minus 4, 6, and 0, and we follow the same process as above. Leading coefficient, the 4 comes down, multiply to get a minus 16, add to get minus 16, multiply to get positive 48, add to get positive 44. Okay, our numbers got a little larger right here all of a sudden. Hold on, that's different from what I got in the answer key. So let me double check everything. So 4, 16. So 4 times 16. Oh, that's why. Because that is not. So that is going to be a, let's try that again. That's going to be a positive 64. So there's the 60. Whoops. All right, back to it. Negative 4 times 60 is going to be negative 240. Adding 6 is going to give us a negative 234. And then multiplying negative 4 times 234 is going to give us a 936. So add that. We end up with a remainder of 936. Whew, numbers quite large there. On the test, the numbers tend to be fairly reasonable. We designed the test, honestly, that could be done without a calculator. This one just got a little large. All right, so this is going to be a 4x cubed, reducing the power by 1, minus 16x squared, plus 60x, minus 234, plus 936 out of another x plus 4. Again, I don't think I explicitly stated above, but the remainder will simply be over the divisor. And we have one more scenario for practice. If you have yet to practice these, I would encourage you to maybe pause and try it. But the 1 goes in the upper left-hand corner. We start with x to the 5th, so we have a 1x to the 5th, 0x to the 4th, 2x cubed, 0x squared, 0x minus 3. And then we'll go ahead and do the computation. Drop the 1, multiply, add to 3, multiply to 3, add to 3, multiply to 3, add to 3, multiply to 3, and then we add to 0. We started with x to the 5th, so we have x to the 4th plus x cubed plus 3x squared plus 3x plus 3. And we don't even really need to say plus 0 over x minus 1 because the zeros will, in the numerator, just leaves it as 0. So there is our answer to 13. All right. 14 and 15, we will use synthetic division to show or prove our work. Again, recall that the remainder is whatever you get when you just simply plug in the number. So again, if the remainder is 0, then we have a 0. If the remainder is not 0, it is not a 0. So 2 is given as a number this time. We're checking if that is a 0, so we'll just use the number as shown. So then the 4x cubed, 5x squared, minus 6x, and minus 4 gives us our setup. And we just go through this and check our remainder. Drop the 4. Negative 2 times 4 is negative 8. Add to negative 3. Multiply to positive 6. Add to 0. Negative 2 times 0 is 0, so we have a remainder of 4. Because that is not 0, our answer to this question is no. All right. Not much different about number 15. I would encourage you to go ahead and try that. And if you get a remainder of 0, indeed it is going to be a 2 would be a 0. All right. In the case of 16, there's two ways you can do this. You can go ahead and find the zeros using the method from 3.4, but this is really more in 3.2. And the hint I want to go ahead and remind you of is to use grouping. And I believe the test, if a question like this appears on the test, which again, basically the review is a practice version of the test, there will be a hint to remind you of this. Grouping works by simply grouping the first two and grouping the second two. And to find the zeros, we would set this equal to 0. So I'll just go ahead and rewrite this on the left. So we have an x cubed plus 5x squared minus 9x minus 45. Set that equal to 0. Grouping the first two, I see they have a common x squared. And grouping the second two, well, I know I'm going to need to pull out a minus 9. And the reason being is if you pulled out that x squared, let's keep things color-coded. So the x squared goes in front. We have an x plus 5 that remains. I need to make sure that when I pull out a number that I also get an x plus 5 there. So I have a minus 9 comes out, and then we have an x plus 5. Still equal to 0. Notice now these two terms are simply separated by addition and subtraction, have a common x plus 5, which will go out in front. And we have an x squared minus 9 left after you divide out the terms. So if we divided that first term by the x plus 5, let's get the right tool, then that would cancel, leave us with the x squared, and divide the second term by the x plus 5, those move out, that x5 moves out, and there's the minus 9. Just to get some space, let's move up to the next column. Realize in red we have a difference of squares. So this is an x plus 3 and an x minus 3, still equal to 0. So our zeros are x equal to minus 5, negative 3, and positive 3. All right. In the last section, we are asked to go ahead and do basically the same thing we did earlier with the factored forms from 3.2. But we're asked to list all possible rational zeros and possibly need to use that to go ahead and find the other zeros. So in the case of these three right here, none of them are factorable. Grouping would not work on this first one. This right here, there's not even grouping. You would really have to kind of rely back on this method. There is a cubic formula, but it's much more complicated than the quadratic. And this one right here, again, this is a quartic. So even if you did group, you wouldn't be able to get a matching parentheses that allows you to finish that process. So So these right here are a little bit lengthy, and yeah, these are our last three. So hopefully you found everything beneficial so far, but let's go ahead and wrap up the review. All right. So the list of all possible rational zeros is you have to look at the factors of the, so I'll just go ahead and start writing. So to go ahead and find the list of all possible rational zeros, you're going to look at the factors. I'm going to need to make my pen smaller, I can tell already. The factors of the -6, the constant divided by the factors of the leading coefficient, which is +1. So ±1, ±2, ±3, and ±6 all divide evenly into -6. And the only thing that divides evenly into 1 are ±1. So you essentially pair all of them up. So 1/1, 2/1, 3/1, and 6/1. These will give you basically the numbers 1, 2, 3, and 6, and again, both the positive and the negative. All right, so now that you have your list of possible rational zeros, you'll go ahead and just pick one of those and try to do synthetic division to find one. I like to start with 1, and let's go ahead and do 1, 2, -5, and -6. So if we were to do this, drop the 1, multiply, add, multiply, add to -2, multiply to -2, -8 is the remainder. Therefore, 1 is not a 0. So again, because the remainder was not equal to 0, 1 is not a 0. Let's go ahead and try -1. And again, you could probably even cheat this a little bit by looking at the answer key. This will work out fine on the test. You will be guaranteed to find a rational zero, so make sure that you are careful with the computation. I've seen basically a page of synthetic division turned on because a little mistake was happening in the computation. So let's try -1. So 1, 2, -5, and -6. And we have dropped the 1, multiply to get -1, add to get 1, multiply to get -1, add to get -6, multiply to get 6, and we do have a remainder of 0. So again, that means that one of our zeros is -1. To find the others, we'll take the quotient. So I'll just take this over here, x squared plus x minus 6. Set that equal to 0, and I'll find the other zeros. Factor this is x plus 3 times x minus 2 equal to 0. We get x equal to -3 and +2. All right, so the zeros here are -3, 1, and 2. Their multiplicity is 1, 1, and 1. So, and again, I think we'll see this in another one of the examples. Yeah, we'll see this in 19, but if you were to see like -1 here and -1 occur like somewhere in this list, then that's when the multiplicity would jump up. So a little typo here, that should have been -1. Okay, at the x-axis, it crosses at each of the scenarios. So it also asks for the y-intercept. The y-intercept, when you plug in 0, is going to just be -6. As stated earlier, everything cancels except for the -6. All right, so let's see. We have a -3, which is right here, -1, and +2. The end behavior is down to the left, up to the right. And again, we've reviewed degree, so you may want to just state that. The degree is 3. Positive leading coefficient gives you down the left, up to the right. And the y-intercept is down here at -6, so I'll put a dot there. We crossed at every 0, so we go up. And we cross, come back down, cross, y-intercept, cross, and there is our polynomial. All right. 18 is very similar. Just remember that you need to go ahead and to do the synthetic division, include the +0 x squared plus 21x and then +20. So just remembering that that is there, you'll go ahead and be able to work with the synthetic division to find the other zeros. In 19, just to see what happens whenever you have the multiplicity from in this type of problem. So the list of possible rational zeros, again, the factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those are all divided by the plus or minus 1, so I'm not going to rewrite that. If you were to go ahead and test one of these, I'm going to test 1. So remember that there is a 0x cubed here. So it's going to be 1x to the 4th, 0x cubed, minus 4x plus 12. And let's see. Drop the 1, multiply to 1, add to 1. Oh, I missed the 9. Hold on. 0. This is the 9. Let's try that again. So that's a minus 9, minus 4, plus 12. So sorry about that. Let's go ahead and check everything else is good. Yeah. So add to 1. You get a minus 8. Then this is minus 8 when you multiply. Add to minus 12. Multiply to minus 12. And we do have a remainder of 0. So this is an x to the 3rd plus x squared plus minus 8x minus 12. Technically, and again, if you kind of play with this, you'll see that this can't be grouped. So I'm going to need to go ahead and find another 0. I'm going to cheat and maybe look at the answer key, but I'm going to need to use 3 as well. So if we set this up with 3, we have 1, 1, minus 8, minus 12, and we end up with 1, 3, 4, 12, 4, 12, 0. So we have now an x squared plus 4x plus 4. And yeah, we can set this equal to 0. So if we set x squared plus 4x plus 4, I think probably to illustrate this better, I should have probably used 2. So let's go ahead and do that. So, well, again, so if you were to use 2 right here, it would, hold on one moment. All right, just was getting a little noisy, so let's finish this off. So if you were to factor this, you would get x plus 2 times x plus 2 equal to 0, and you would add x equal to minus 2, minus 2. So you wouldn't write that twice, you would just bump up the multiplicity. So our zeros here, where 1, let's put it in order. So minus 2, 1, and 3. The multiplicity, in this case, as stated here, you wouldn't write this twice. It would just be have a multiplicity of 2, then 1, then 1. Okay, then the x-axis, it would touch and turn at negative 2. It would cross at 1 and 3. The y-intercept is 12. And again, you could make the observation, because it is an even degreed polynomial with a positive leading coefficient, you will go ahead and fall to the left. Well, let's actually put the negative 2 here, put the positive 1 and positive 3. So even degree, you're going to rise to the left and rise to the right. Then you'll come down, touch and turn there. You'll go up, hit 12. So I'll just say 12 there. Come back down, cross, cross, and there it is. All right, so this is a test where a lot of things need to be put together to do well. So go ahead and do the review multiple times until you are successful in understanding every single step. If you have questions, be sure to reach out. But good luck, have fun, and study hard.